Hi guys, we're doing the A2 Maths paper today, Pure 3. So we'll get started. So the first question, now they're very fond of these questions where they ask you to solve something involving absolute values. Now you can be careful about it and think about things being, you can make two separate equations, one for plus and one for minus, or you can do the easy way, which is just to square everything. And you will in general get two answers through both, the same answers through both methods. So I'm going to do the easy way, which is squaring. So if I square both sides, I will get x squared plus 4 minus 4x, and that's equal to 1/9 x squared. And then I rearrange, and I will I multiply everything by 9 and then rearrange, so I will get that 2x squared plus 9 minus 9x is equal to 0. So I've just multiplied by 9 and then divided by 4. And then this you can easily solve as a quadratic, easily factorized, and you'll get that 2x minus 3 times x minus 3 is 0, which of course means that x is either 3/2 or 3. And you would get exactly the same answer if you were careful and said that, x minus 2 is equal to plus 1/3 x, or x minus 2 is equal to minus 1/3 x. And you can see that you would get the same answers both times. So let's look at this one. So this is one of those sort of iterative, very, very dull and boring iterative questions. So you can see how it works, right? If I give you some seed, some initial value x1, you can use this formula to give me x2. And then x2 will be, you plug into there again, and you'll give you x3 and x4 and so on. So the first question is asking you to do that. And they want you to get alpha correct to 4 decimal places, which is the same thing as when the first 4 digits after the decimal place stop changing. So I'm not going to do this here because this is just robot work, but you just keep plugging in and you keep writing down your answers, x1, x2, x3, so on, until you notice that after the decimal point, the last 4 numbers do not change after a couple of iterations. It's getting more and more accurate, and you only need accuracy up until the first 4 decimal places. But you need to write them out to 6 decimal places for the examiners to see. So now what does it mean for this to converge, this equation we have here? Well, if it's converging, if after a while it converges in the same number, that means that xn, so convergence, means that at some stage xn is basically going to be equal to xn plus 1, because even though that's what it means to converge. It means that each iteration of this formula gives you the same answer. So this is like at an infinite point. After an infinite number of terms, you finally converged. With a finite number of terms in the series, you're not going to be quite converged. There'll still be something like very deep in the decimal points where they start changing from each other. But the limit, as you've taken this n to infinity, is that xn is equal to xn plus 1. So I'm going to call this alpha. And therefore, alpha will satisfy the equation where xn is equal to xn plus 1. So xn was on the left-hand side. Sorry, xn plus 1 was on the left-hand side, and xn was on the right. So I'm going to call them both alpha and just write it like this. And we can just solve this. If you put it on the rearrange it, you get that alpha cubed plus 100 is equal to 2 alpha cubed plus 50. So alpha cubed must be equal. If you rearrange, take that alpha over there, take that 50 over there, you get alpha cubed is equal to 50. and therefore that, alpha is the cube root of 50, because they ask for the exact value. So exact means sort of no trailing decimals. So you keep it in forms of surds, or as it may happen, logs, or whatever it is. You don't put the actual value that you get out. Okay, question 3. So we're given an equation that relates y to x, exponential equation, but then what we've graphed is natural log of y, ln y, versus x squared. So that's what these values are, and that's very important to remember, because this value here, 0.64, that's not the value of x, that's the value of x squared at that point. And this 0.76 isn't the value of y, it's the value of ln y. So let me take the log of both sides, the natural log of both sides, and I get that ln y is equal to, and you need to use the laws of logarithms here. You get natural log of a plus ln of e to the minus kx squared. The natural log cancels with the e, so this is equal to ln a minus kx squared. So if we call this axis a and this axis b, we can write the equation as a is equal to natural log of big A minus kb. So we really don't care about right now about the fact that a is the natural log of y, because we're given the value for a, for the natural log of y itself, and the value for b, which is the x squared, not x itself. So this question can confuse you if you don't remember that. So we're given 2 points, and we need to solve for big A. So that's easy. So for the first point, we have that 0.76 is equal to ln A minus k times 0.64. And for the second point, we have that 0.32 is equal to ln A minus k times 1.69. Now, if I subtract these two equations, I'm going to get rid of the ln A's. And so that will give me that like 0.76 minus 0.32 is equal to ln A minus ln A minus k, 0.64 minus 1.69. And this can easily give you k. And now we need to solve for a. So instead, that's the minus 1. And now the plus 1, I get that 0.76 plus 0.32 is equal to 2 ln A minus k, which we already got. So that's 0.42 times 0.64 plus 1.69. And you can easily, you get this in terms of ln A is equal to blah, blah, blah. And then A must be equal to e to the power of whatever that blah, blah, blah was. So that's all there is to it. So the big trick in this question is not being confused by the way they've done it, but realizing that the variables that you need are ln A and x squared, not y and x. Okay, question 4. So we're given this polynomial, and this question is all about factorization and like division in a way. So there's a few ways to do this kind of thing. But when you're told that some bracket is a factor, it means that the solution to this bracket being 0 is a solution to the equation being 0. So what do I mean by this? I mean that x equaling minus a third gives p of x equals 0. So let me plug that in. Or rather, x equal to minus a third is a solution, as we say, to the equation this is equal to 0. So if I plug that in, I get minus a over 27 minus 20 over 9 minus a third plus 3 is equal to 0. And therefore, you get that a plus 60 plus 9 minus 81 is 0, and then a is equal to 12. So that's pretty simple. So saying it as a factor means that both of them are solved by that value of x, as in they make the thing 0. So now they want us to factorize the thing completely. And as I say, there's a couple of ways of doing this. Now, I think it's the easiest way is to create a generalized equation and then solve it. So I'm going to say that p of x, so when a is equal to 12, p of x is equal to 12 x cubed minus 20 x squared plus x plus 3. And I'm going to say this is equal to 3x plus 1 times a bracket with 1 degree lower polynomial x. So let me call that bx squared plus cx plus d. And I'm going to multiply this guy out, giving me 3bx cubed plus, now look for the x squared terms, 3c plus b x squared plus, and then the x terms would be 3d plus c x plus d. So you can see immediately that b is equal to 4, because you're comparing coefficients of values of x. So 3b must be equal to 12, so b must be equal to 4, and d must be equal to 3, because it's the only thing that's not got an x in front of it. So we already have 2 of them. And then we know that 3c plus b, which, because we know b is 4, is 3c plus 4, must be equal to minus 20. And that means that c is equal to minus 8. So therefore, there we got it. We got b, we got c, and we got d. And you can just write that out as your solution. Okay, question 5. So this question is all about implicit differentiation. We're told that this curve obeys this parametric equation. And what that means is we're not given an equation that's in the form of y is equal to blah. We're just given an equation relating y and x that is true for every point. So a maximum, if we imagine that we did have an equation of the form y is equal to blah, 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 how would we find the maximum? Well, we take the derivative, right? So we can do the same thing here. And we know that maximum means that dy dx is equal to 0. So let's do some implicit differentiation. So what we'll do is we'll just differentiate this whole thing with respect to x. Okay, so even though it's not dy dx, we're just differentiating all of this. Why don't we call this, we'll give it a name, we'll call this f of x. And we want, and that's equal to 0, and it's equal to all of this stuff. So we want df dx. And if we look at the first term, well, that's easy. That's just 3x squared. The second term is a little more complicated. So firstly, you might think that you just get the term y squared because you've differentiated the x. But the thing is, y is a function of x. So you need to use the chain rule. And so this first term is me differentiating this bit. And now I'm going to differentiate the second bit using the chain rule. So I've used the product rule and I've used the chain rule. So the derivative of the derivative of y squared is dy squared dy dx, which is 2y dy dx, you see? So this is using the chain rule. And so that second bit, that x squared bit, also needs to be differentiated using the product rule. And again, here we have plus 2ay dy dx minus 6ax. And this is equal to the derivative of the number 0, which is just 0 again. Well, we know that dy dx, it must be equal to 0 at this point. You know, that's infinitesimally not changing with y there. So these things we can throw away. And we get this relation, 3x squared plus y squared minus 6ax is equal to 0, which equivalently is that y squared is equal to 6ax minus 3x squared. And now I want to know something about that point. So this this is true at that point. So I can plug that back into my equation, which is true for all the points on the curve. And wherever I see y squared, I plug in this thing again. So I get that x cubed plus x times 6ax minus 3x squared plus a times 6ax minus 3x squared minus 3ax squared is equal to 0. Okay, we're almost there. Now I just need to multiply some stuff out, and I will get that x, I have x cubed, and then I have, how many of them? I have one here, and then I've got another one there, minus 3. And my x squared terms, well, I've got one guy here, 6ax squared, and another one there, minus 3a, and another one there, minus 3a again. Plus, what x terms do I have? Well, that can't be it, that can't be it, that can't be it. Here's one, 6a squared, and there's no more. That's equal to 0. Now we see that this guy vanishes. It'll cancel out. So I got minus 2x cubed plus 6a squared x. And if I take a factor of a 2x out, I get 3a squared minus x squared. So you see that either x is equal to 0 or x is equal to plus or minus the square root of 3. And that reflects the various different points, which this thing can be a minimum. And what we want is the positive square root of 3 answer, as you can see just by looking at the thing. Sorry, square root of 3a. Whoops. So x is equal to plus the square root of 3a, and that's our final answer. Okay, question 6. This is just sort of crunching through the differentiation of trigonometric functions and using some of the identities that are in the formula booklet. So 1 over cosine of x, which is equal to sec x, that's what it's called, and we want to differentiate it. So we want to use the chain rule or the quotient rule or whatever it is that you like, but I like to use the chain rule. So this is going to be minus 1 over cosine squared x times the derivative of cosine of x, which is minus sine x. So this is just, sine over cosine squared, which is tan over cosine, which is tan x sec x, as they asked for. So for this, all we've used is that tan is equal to sine over cosine. So that's the first one that we need to use. It's in the formula booklet. And now, excuse me, now they want us to use this information to differentiate this function. So dy dx is going to be equal to 1 over sec x plus tan x by differentiating the logarithm times the derivative of whatever is inside. Well, the derivative of sec x, we just worked that out. That's tan x sec x. And the derivative of tan x, we can find from the formula booklet, is sec squared x. So if we take a sec out, then we get tan plus sec all over tan plus sec. We cancel. It's just equal to sec x. And all that we really need to know here was that the derivative of tan is sec squared, which we already have. Okay, now we're going to use this information and we're going to solve this this integral. So very, very common in physics and maths is to use some sort of angular variable and substitute in, because it makes a lot of things a lot easier. So thankfully they've told you what they want you to substitute. It's very much harder when they ask you to come up with a clever substitution. So firstly, I'm gonna adapt this thing to use theta instead of x. So to do that, I know that x is square root of 3 tan theta. Therefore, dx is equal to square root of 3 sec squared theta d theta. Great. And I also know that when x is equal to 3, theta is equal to, and then you can use your calculator to solve this. It's going to be like the inverse tan of square root of 3 or something. And theta is equal to pi on 3. And when x is equal to 1, theta is equal to pi on 6. So these are the limits. So when you adjust, when you change variable in one of these integrals, you need to change the actual variable. You need to change the measure, is what it's called, integration measure, and you need to change the limits as well, because x is equal to 3 corresponds to a place where theta is pi on 3. So let's do that. So now we have an integral from pi on 6 to pi on 3 of 1 over square root of 3 plus 3 tan squared theta. And dx becomes square root 3 sec squared theta d theta. And we notice immediately that the 3's will all cancel, because you can take a square root of 3 out of here. And for this we have to use the identity that 1 plus tan squared theta is equal to sec squared theta. And that's in the formula booklet. And that gets square rooted, so you have a sec theta underneath. And so the whole thing becomes integral pi on 6 to pi on 3 of sec theta, excuse me, sec theta d theta. And now we use what we did before, where we differentiated something and got sec x. Well, now we're integrating, so we go back. So this is going to be equal to, and we have integrated it now, the natural log of sec theta plus tan theta between pi on 3 and pi on 6. So this is equal to, if we plug in the values to our calculator for sec and tan, it doesn't look too bad. Natural log of 2 plus square root of 3 minus natural log of 2 square root 3 on 3 plus square root 3 on 3. And if you pull these all together using the laws of logarithms, you get that this is the natural log of 2 plus square root 3 all over square root 3. Great. Okay, question 7. Trigonometric identities, all in the formula booklet as per usual. And they've given you the hint. They've said by first expanding. So let's expand this to start with. So we get that the cosine of x plus 45 degrees is cosine of x, cosine 45, minus sine of x. Remember, for the cosine of summing rule, the sign flips. Sine x, sine 45. But we know that both cosine of 45 and sine of 45 are the same, and they're both 1 over square root 2. Fantastic. So now we're going to add we're going to subtract square root 2 sine x. So if we do this, we get so the cosine of x plus 45 minus square root 2 sine x. And it's going to be equal to 1 on square root 2 cos x plus sine x. And then I'm going to bring this guy inside, and it's going to become, oh wait, sorry, this should be a minus. Minus. And there's going to be minus another 2 copies of sine of x, because of I brought it inside the 1 over square root 2. So if you multiply it out, 2 over square root 2 is square root 2, and it all works out. Now I'm going to say this is equal to the expansion of this guy. So that's r times cosine x cosine alpha minus sine x sine alpha. And I can equate the coefficients of cosines and sines in the same way that you can equate real and imaginary numbers, it's because they're completely independent. It all comes from, types of waves, and the fact that you can't build a cosine wave from sine waves, like pure sine waves. They're completely independent things because they've got this phase shift. I mean, it's signal processing really, but the point is that you can just equate the coefficient. So here it's the coefficient of cosine of x here is 1 over square root 2, and that's equal to r cosine alpha. And for the sine of x, it's 3 over square root 2 is equal to r sine of alpha. So to get alpha, I'm going to divide this guy by this guy, and I'm going to get that the sine of alpha over the cosine of alpha, which is equal to the tan of alpha, is equal to 3. And if you put this into your calculator, you'll get that alpha is equal to 71.6 degrees, which is perfectly fine in our limited space, and there's no other values of alpha that are in that range. Now for r, I go the other way, and what I do is I square both of these and then add them. So I get that r squared cosine squared alpha plus r squared sine squared alpha is equal to 1/2 plus 9 halves. And you see that this becomes r squared sine squared plus cosine squared, which is just 1, is equal to that. And then you just take the square root and you get that r is equal to square root 5. So these are the ways of putting things into, in finding like this coefficient out the front, as you sort of square them, and then you realize that cosine squared plus sine squared is equal to 1, which is a very important identity that is in the formula booklet. Okay, hence solve this equation. So we're going to use this info, and we're told that all of that business is equal to 2. So this thing is just r cosine of x plus alpha, right? So we have that square root 5 cosine of x plus 71.6 degrees is equal to 2. And here's where you need to be really, really careful, because you remember all these things where you're trying to find solutions and there's trigonometric functions, and there turns out to be several solutions within the range. Now this is even harder than that, because the thing that is the argument of the cosine, like the thing that's actually varying, is this x plus 71 over 6. So what I'm going to do is I'm going to call this, I don't know, A. So I'm going to find solutions for A, and then I'm going to use that to find solutions for x. So this is square root 5 cosine of A is equal to 2. And I need to change my limits, right? I need to work out what the range of A is if this is the range of x. Well, that means that 0 less than x is less than 360. Well, this corresponds to this range. So if x got to be greater than 0, then x plus 71.6 must be greater than 71.6, and the same for the other one. So this thing is A. So this is my range for A. And now I can proceed. And if I plug this into my calculator, I will get that A is equal to 26.61 degrees. Well, that's not in my range. So what's happened is that the calculator is, so actually I'll draw it this way. This here is 360, here's 180, here's 90. So here's my limit. So this is A, remember? That's the thing which the cosine is actually looking at, is A. That's my cutoff on A, and likewise somewhere here. So what it's done is it's picked out this point, because that's where the cosine is equal to 2 over square root 5. But that's not the points that I'm interested in. I'm interested in this same points which also give 2 over square root 5, but are over here. And so you'll notice that what I can say is that this is that 26.6. And these ones are sort of the same distance away from 360. So actually, A is equal to 360 minus 26.6, or A is equal to 360 plus 26.6. And that will give you that, and these are both valid values. And then you get the values for x. So x will then be equal to like 261 or 315 by plugging in that A is equal to x plus 71.6. And that's what you have to do. It's just a little bit trickier here, but as long as you think through it and realize what is it that is actually periodic. It's the cosine function. What is the cosine function taking? X plus 71.6, not x itself. So best way to think about it is thinking of this as its own variable, solve for that variable, work out which answers lie within the range that you're interested in, i.e. these ones, not the other one, and then use that use the calculator's information to find those, and then solve back for your original variable. Okay, question 8. This is fairly straightforward. This is a technique of factorizing things using partial fractions, and it's very, very useful in integration, as we will see in the next section of the question. But what they've done is they've taken the denominator and they've divided it up. But you see that they've divided, it isn't just x squared and 2x plus 1. You also need a 1 over x, because that is something that could contribute if you are drawing all this together back into a single fraction. So if you're doing it yourself, if they haven't given you already the partial form like this, then you must remember that you have to have every potential power of x that might contribute to this thing. So what we need to do is draw this back into a single fraction. So we have a times 2x plus 1 plus bx 2x plus 1 plus c cx squared all over x squared 2x plus 1. And I'm just going to look at the numerator here. And this gives me, for powers of x squared, I have b, I have 2b and a c. And then for x, I have the 2a plus b. And then for a single number, I only have a. So I compare this and I realize it has to be equal to this. And therefore, a must be equal to 1. 2b must be equal to minus c. And 2a, which is equal to 2, must be equal to minus b. So b is equal to minus 2. And then if I look at c, c is therefore equal to 4. So those are the three. Oh dear. I don't know why it does that. Those are the 3 equations you need. Okay, so now we're going to use this. And we're going to solve this equation. So I'm going to integrate y dy, 1 over y, so separation of variables again. So I'm going to take this y over there and take all this x business over there and the dx, separation of variables. So integral of dy over y is equal to the integral dx over x squared 2x plus 1. And this is equal to, as we've just found, 1 over x squared minus 2 over x plus 4 over 2x plus 1. Well, what about the limits? And you remember that there are 2 different ways to use these limits to get the correct equation. You could either solve it indefinitely and then add a plus c at the end and then plug in the limit, this sort of y is 1 when x is 1 factor, and that's perfectly fine. I prefer to do it where you actually sort of incorporate it into your process by using it as one of the limits. So my lower limit I'm going to say is 1, y is 1, and then I'm integrating up until some higher y of x. And the limits have to match on my x side. So when y is 1, x is 1. And when y is y of x is x. So this guy on here, well, he's just going to be the natural log of y between 1 and y. And that's going to be equal to minus 1 on x minus, minus 2 natural log of x plus 2 natural log of 2x plus 1. And you can convince yourself that that's the correct integration between 1 and x. And this is going to be natural log of y minus natural log of 1. Natural log of 1 is just 0, because the natural log asks you e to the what is equal to 1. Well, e to the 0 is equal to 1. 1. As anything to the 0 is 1. So any log of the number 1 is going to be 0. And this is going to be equal to we can just do that quickly. Minus 1 on x minus 2 ln x plus 2 ln 2x plus 1. And then the plus 1 minus 2 ln 1, which is 0, minus 2 ln 2 times 1 plus 1 ln 3. So this is the general form. And now they want us, well, there's not much space. I'm going to make this a bit smaller. And now they want us to plug in, find the exact value of y when x is equal to 2. And remember that word exact, meaning no decimal points or anything. So they want a general expression. And they want it without any logarithms in it. So let's just see how we go. So we know the natural log of y when x equals 2 is minus a half minus 2 ln 2 plus 2 ln 5, just plugging it in, plus 1 minus 2 ln 3. And this is equal to, and I'm going to put everything in terms of logarithms. And you may think, well, how can you put a number in terms of logarithms? Well, it's easy. You just say, you just do this. You just say that 1/2 is equal to the natural log of e to the 1/2. Or you can think of it as, just 1 is equal to natural log of e. And so 1/2 is equal to 1/2 times 1, which is equal to 1/2 times ln of e, which is equal to ln of e to the 1/2. All of these things are equivalent. So this thing is equal to ln of e to the minus 1/2, minus 2 ln of 2 plus 2 ln of 5 plus ln of e minus 2 ln of 3. And I'm going to bring all the logarithms together, which gives me, I'm going to bring this 2, this becomes 2 squared, that becomes 5 squared, this becomes 3 squared, and so I have the natural log of 5 squared times e to the 1/2, because this 1/2 and this is e to the 1, so 1 minus 1/2 is 1/2, over 2 squared times 3 squared, which is the natural of, what was it? 25 over 36, e to the 1/2. And now we want an equation for y, so I just take raise both sides to the power e to the power of both sides, and get y is equal to 25 over 36 e to the 1/2. And that does not contain any logarithms. So give you a value of y in a form not containing any logarithms, they mean you got to get the y out of the ln there. And that's the solution. Okay, question 9, complex numbers. So this one is pretty straightforward. The best thing to do here is to say that w is equal to x plus iy. And we have that w plus 3w star is equal to iw squared. And remember that w squared does not equal to w times w star, which is that guy. So if you see the mod signs, that means you actually take the complex conjugate and multiply it by the original. W squared just means you take the original twice. So let's see, what's w? Well, it's x plus iy. What's 3w star? Well, that's plus 3x plus minus 3iy, because w star is, you just flip the sign of the I, is equal to I times w squared, which is x squared, plus 2ixy minus y squared, because you square the I and that becomes a minus. And now I'm going to equate real and imaginary parts on both sides in the same way that we equated cosines and sines before. And that's because, they're independent. It's the same thing. It's like a vector, really. It's like a real part and imaginary part being stored in a two-component vector. They're completely independent sort of dimensions, really, in this Argand space. So you can move independently in x and y. So you can compare them, not x and y in terms of this x and y, but imaginary and real. Anyway, what's real on the left-hand side? Well, it's 4x. And this is equal to what's real on this side? Well, there's an I in front, so I needed to sort of cancel with the other I. This is minus 2xy on the right-hand side. And these two things are equal. So y is equal to minus 2. And now, what about the imaginary parts? Well, on this side, we've got 1 minus 3, which is minus 2y. So this is real. This is imaginary. On the left-hand side, and on the right-hand side, we've got x squared minus y squared. So the imaginary part means whatever it is that's multiplying I. So you don't include the I. And we know that that y is equal to minus 2. So this means that 4 is equal to x squared minus 4. So x is equal to plus or minus the square root of 8. But we're told that x is greater than 0 because x is the real part of w. So therefore, x must be equal to the positive square root, which is it's 2 square root 2. And that's all there is to that question. Okay, so this one's a little more of an art. Is really realizing how to do these ones. So you're given two conditions, right? And usually there'll be one involving the sort of modulus thing and one involving an argument. So you should remember that the modulus of a complex number, so a complex number can be written as the modulus of the number times e to the I times the argument of the number. And the modulus is x squared plus y squared if w is equal to x plus iy, and the argument is inverse tan of y on x. And if that seems unintuitive to you, it's all to do with the Argand plane and the way that we represent things on a circle. And this is r, and this is the argument, theta, let's call it. But this is the x-coordinate, and this is the y-coordinate. And it all comes in the same way that you would convert from Cartesian to polar coordinates. If you haven't sort of seen that derivation before, I'd recommend going through it and convincing yourself that this is true, that point can either be represented in this sort of what's called polar form or in Cartesian form, x plus iy. Anyway, so we're told that z minus 2i is less than or equal to 2. Now, I mentioned thinking of the coordinates in the Argand plane, so there's x plus iy, the coordinates being x and y, the real and imaginary parts, as a vector, coordinate, a vector. So really, z in this case is like this. And we're subtracting another vector. This 2i, that's just another vector. So minus 2i is just the vector 0 minus 2 in this space, in the Argand space. So what we're saying is that the difference, so you know, if you subtract two vectors, one vector from another, you're kind of getting the vector between them, if you remember that. So what this is saying is that the distance between these 2 points in the Argand plane is always less than or equal to 2. So whatever your z is, you're always less than distance of 2, less than or equal to a distance of 2 away from the point minus 2, 0 minus 2. So visually, that's a circle, right? A circle is the locus of all points a given distance from a center. And in this case, that, sorry, it's plus 2i. So I'm taking the difference between z and 2i. So it's z minus 2i, but the vector itself isn't 2i. So where is that locus? Where's that center of the thing? Well, it's at 0, 2. So this is kind of what that circle looks like. Oh dear, forget that. Anyway, it has a radius of 2, and it's centered on 2. So therefore, it touches 0 there. So that's what it's going to look like. So this is the imaginary, and this is the real in the Argand plane. Well, that's done. Now, what about the other one? So this is saying that the argument of z plus 2 is between these two limits. Okay, so this was the first one. So now the second one. Well, z plus 2, well, that's just xy plus 2, 0, because 2 is just a sort of a vector with no imaginary part, only a real part. So remember when I said that the argument is equal to the inverse tangent of this stuff. So the argument of z plus 2 is the argument of x plus 2y, which is going to be equal to inverse tangent of y over x plus 2. And we know that this is between those two limits. So I can say that if the inverse tangent of the stuff is less than 0, then the stuff must be, greater than 0, stuff must be greater than the tangent of 0, which is 0. So I have that, my first limit is that y over x plus 2 is greater than or equal to 0. And that just means that y is greater than or equal to 0. Now I also have the other limit. I have that y over x plus 2 is less than or equal to the tan of pi on 4, which is equal to 1. So I have that y is less than or equal to x plus 2. Well, these are just two straight lines, right? So I know that y is greater than or equal to 0 means I must be above the y is equal to 0 line. And y is less than or x plus 2 must mean I'm below the line y is equal to x plus 2. So we finally can pull it all together. And we have our Argand plane, and we only care about what's above the y-axis. And here's 2. And here's my terribly wonky circle. It's not all my fault. This pen is a bit weird, and that does touch the x-axis. The x-axis, yeah. So we have this line, which is the x-axis, which is our one limit. And then we have another line going like so, which is this line here. And we know that the points must all be within this section. And we're done. We're finally done. So that's what it is. And these things will always require you, the best thing to do is to express them as x and y and think about this polar form and the formulas for working out the modulus, which is like a radius, a distance, and working out the angle, and converting them into sort of equations in x and y, which is what the Argand plane is really all about. All right, question 10, vectors. So vectors and planes. So we're given two vectors. We have A is, I'm going to write it in my way, 2 minus 3, 2. And we have that B is equal to 5 minus 2, 1. And we want the position vector of the point of intersection of the line through A and B and the plane P. Well, we know that anything in P obeys this equation. And so vectors, so points in P, we'll have position vectors that look like x, 5 minus x, and some z coordinate. So there's no restriction on the z coordinate when you're on the plane P. So you can just put any one of them there. Now I'm going to look the line through A and B is contains the vector AB, and this is just B minus A, as we know, and that's going to be equal to 3, 1, minus 1. And they intersect when the line A plus lambda AB satisfies P's equation. Now just take a moment and be sure that makes sense to you. I have some line that goes through A and B. So to get to any point in that line, I will go to A, and then I will go up and down the line between A and B. Maybe I go to B, or maybe I go further along, but I still have, this is a vector in the direction of the line. So this will take me on that line. And when I reach a point that satisfies the equation for P, then I'm on the plane as well. Then the line has hit the plane. So I have the A plus lambda AB is 2 plus 3 lambda, and minus 3 plus lambda 2 minus lambda is equal to x 5 minus x z. And this immediately tells me that lambda is equal to 3 over 2. And then I can just plug that in. In fact, I only needed to do it for one of the coordinates because I'm already sorted. So this is that point, right? So I plug that in, and I get that the point is 13 on 2 minus 3 on 2, 1 on 2. Okay, a second plane is introduced, and it's got this equation. So now z is you do have restrictions on what your z can be, so it's not quite as simple as before. And we've got 3 unknowns. We've got B, C, and D. So we need 3 equations. Well, what do we know about this plane? Firstly, we know that it contains the line AB. Therefore, the plane contains A and B, right? Makes sense. So therefore, A and B both satisfy this equation. So for A, I get the equation. So I plug in the coordinates of the point A, and I get that 2 minus 3y plus 2z is equal to D. And it's important to really think about what this plane looks like in terms of in the space. These restrictions all remove a degree of freedom. You move around in the space freely, and then you're told that you have to obey a certain equation. Well, that removes one of your degrees of freedom. And the more equations you have, the more your degrees of freedom are restricted, and it lowers the dimensionality of your space. Now, don't worry about this too much, but I feel like it's important to think in terms of equations and degrees of freedom. And you know that if you have 3 unknown things, you need to have 3 equations to tell you what they are. And they tell you how you've restricted your space. So anyway, here's one equation. And what I've done is I've taken the point A, because I know that A is on the line. I've plugged it into the plane, this new plane. I've plugged it in, and I'm going to do the same with B. And I know that B must also obey this equation. So 5 minus 2 oops, this is not y, and that's not z. Oops, that's b and c. So 5 minus 2b plus c is equal to d as well. And I'm going to take 1 and subtract 2, and that's going to give me minus 3 minus b plus c is equal to 0, which is equivalent to c is equal to b plus 3. And then I'm going to take 2 copies of 2 and subtract 1. And that's going to get rid of the c's for me. And so I get that 8 minus b is equal to d. 3d, whoops, 3d. Wait, not 3d, just d. Right. So what we have 2 equations here, but we need one more. And we have to use the fact that the angle between P and Q is 60 degrees. So if the angle between the 2 planes is 60 degrees, that means the angle between their normals is 60 degrees. Well, normals you just find by using the coefficients in front of, if you're given the constraint equation, you're asked to find the coefficients before x, y, and z. So the normal to Q is 1, B, C. And the normal to P, well, that was going to be equal to 1, 1, and 0, because there was no constraint on the x in this equation here. So just 1, 1, and plus 0 times z. Sorry, z. So if the acute angle between the planes is 60 degrees, that means that we can use the dot product. So the dot product between the normals is 1, 1, 0, dotted with 1, B, C. And that's equal to 1 plus b. And this is equal to the magnitude of the normal, which in this case, in case of p, is square root of 2, times the magnitude of the other normal, which is 1 plus b squared plus c squared, times the cosine of the angle between them. So now I can, I'm going to square both sides. So I get 1 plus b all squared is equal to 2 times 1 plus b squared, and I'm going to substitute in the value I found for c from before, which was b plus 3. This is plus b squared plus 9 plus 6b, times the cosine of 60 degrees squared is going to be 1 on 4. Multiply this out, I get 1 plus 2b plus b squared is equal to blah, blah, blah. And after all of this, we get that if you just rearrange, and I mean, you find that the b squareds will cancel, and you arrange, you'll get that 2b is minus 8. And so you'll have that b is equal to minus 4. And then you can use that to solve for the C and D. And that's it. I hope you have found this helpful. Please let me know if you have any questions or comments, and I will see you soon. Bye.